Hi, my name is Kevin Chu. The topic of my talk is enabling accurate coarse-grained atomistic simulations of defect behavior in random alloys. With the development of multi-principal component medium and high entropy alloys comes a rejuvenated interest in solute strengthening. The critical solute dislocation interactions and rough potential energy landscape that give such alloys their strength are essential to capture in atomic scale simulations. Simultaneously, modeling dislocation behavior in recent MD studies has revealed the necessity to use extended dislocation line lengths to achieve convergence, making full MD simulations costly and time-consuming. In this talk, I will describe our recent efforts to model dislocation mechanisms in a concurrent multi-scale modeling framework, the concurrent atomistic continuum approach. Controlling solute dislocation mechanisms can be summarized as follows. The atomic size misfit or misfit volume lead to locally fluctuating compressive or tensile stresses, same mechanism as in traditional alloys. Then, hinting at strong solute pair bonding regions across the glide plane, add additional chemical barriers to dislocation glide. Finally, processing methods, such as AM with high thermal or stress gradients, may lead to the clustering or ordering of solutes on the order of a few nanometers, and this is also shown to lend additional hardening effect. Resolving the atomic level detail of these solute interactions is necessary to adequately describe dislocation-mediated plasticity in multi-component alloy systems. Further reinforcing this fact is the recent literature simulating alloys using average atom interatomic potentials. These essentially embed the average response of the alloy, assuming a fully random arrangement of solutes. The elastic constants and the energetics at a given target alloy composition are reproduced. The table at the bottom shows elastic constant comparisons calculated using two iron-nickel-chromium potentials, comparing true random and average atom values. At the left, the generalized Stakenfall energy curve is shown for a similar comparison. Mixed potentials can also be defined that define average atom and true solute interactions. All the energetics show close agreement. The results on the left, though, show a stress-strain comparison of a medium entropy alloy, simulated using average atom and true random interatomic potentials. The yield behavior is notably different, with the average atom curve underpredicting alloy yield stress and ultimate tensile stress. On the right are dislocation and mobility curves calculated using true random and average atom representation. Without the true random solute representation, there's nearly no threshold stress, like a negligible Pearl's barrier in a pure metal, and the dislocation velocity is similarly much higher due to the lack of the locally varying energetic barriers. Thus, it is the nuanced detail of the nanoscale fluctuations of site-to-site solute differences and solute dislocation core interactions that are the true limiting mechanism in such a system, and not the bulk elastic or energetic response. Thus, fully true random simulations need to be executed to assess dislocation behavior. For example, mobility in an iron-nickel-chromium alloy. The authors discovered that a minimum periodic dislocation line length is required to get converged behavior. Below this minimum line length, there is a start-stop displacement due to pinning along the dislocation line that can be observed in the figure at the bottom left. Similarly, the right plot illustrates a large deviation in the dislocation velocity below a minimum critical system size, with multiple random alloy instantiations required to assess the validity of your dislocation and mobility result. The minimum line length is also found to be sensitive to both the temperature and applied stress range. Thus, the resultant set of full MD studies becomes extremely costly. Multi-scale modeling approaches must satisfy the requirement of solute composition fluctuation dependence and access the extended length scales required for converged calculations. Coupled atomistic dislocation dynamics approaches, CAD, use force or energy-based coupling to bridge fully atomistic domains to continuum domains. Also, recent composition-dependent discrete dislocation dynamic simulations describe discrete dislocation line segments and represent solute concentration dependence by randomly sampling the composition of regions in different voxelized volumes. In the CAD approach, a coupling pad region where atoms and finite element nodes overlap is employed to bridge discrete to continuum representations. Various procedures are required to resolve the difference dislocation representation, atomistic to continuum, and significant spurious stresses develop from this coupling. Even in single component pure systems, these stresses exist. Introducing random solute speed further exacerbates this issue, even in the absence of a dislocation or a defect. Drawing your attention to the bottom left plot, the stress fluctuations in an iron-nickel-chromium alloy across the coupling pad region CAD simulations is nearly 100 megapascal. Introducing a dislocation with varying local curvature and stress remains to be examined with this approach due to such limitations. On the other hand, composition-dependent DD can also capture the effect of composition, with dislocation line segments becoming wavy due to varying voxel elastic properties. The issue is that due to the length scales of these voxels, mechanisms cannot truly be compared to a solid solution. In addition, DDD does not represent the detailed energetics of solute dislocation core interaction. The volume voxel resolution employed is on the order of tens of nanometers. Thus, it's more similar to describing dislocation interactions at large obstacles. A multi-scale method, then, that accurately represents discrete solute fluctuations and is able to reduce the degrees of freedom without sacrificing accuracy has not previously been demonstrated. We've recently shown, however, that the application of CAC, the concurrent atomistic continuum method, to this problem domain is a promising choice. The foundation of CAC is atomistic field theory, which links atomistic continuum level representations of a material based on Irving and Kirkwood's formulation for local densities, in a simultaneous lattice plus basis representation of a crystalline material. In CAC, the only constitutive relation required is the interatomic potential. This formulation allows for atomic resolution degrees of freedom target regions such as the dislocation core or glide plane. And coarse-grained finite element representations can be employed elsewhere to reduce total degrees of freedom in the system. Due to the finite element definition in CAC, dislocations can also be propagated into the conjugate gradient into the coarse-grained region, along slip plane-oriented finite elements, as shown on the bottom left, with no heuristic treatment as required in CAD, no mesh refinement. This is also shown schematically at the bottom right. Previously, CAC simulations were executed in single component systems or pure bilayers. The use of average atom interatomic potentials with mixed average atom and true random interactions now allows for the representation of bulk alloy response in the coarse-grained region, and true random full atomic degrees of freedom can be employed as necessary. This can conceptually be recognized as a two-level spatial and chemical coarse graining or homogenization. This is shown in the figures below. On the bottom left, a dislocation resides in the true random atomistic degrees of freedom region, enabling the calculation of the critical solute dislocation interactions motivated earlier. Degrees of freedom away from this dislocation core can be coarse-grained, and an average bulk response is sufficient. The model at the right is constructed to compare directly with CAD simulations with a distinct atomistic to continuum interface degree of freedom transition region. You can also note that there is no pad region required in CAC, overlapping atoms and nodes, because there is no coupling relation. True random atomic degrees of freedom interact directly with nodes through the interatomic potential in the CAC formula. In these models, we use element sizes that represent nearly 2,000 atoms per element. We demonstrate that the spurious forces are completely eliminated across the atomistic to continuum interface. If you recall the CAD results, standard deviation in the principal stress components reached nearly 100 megapascals. Here, it's significantly below that, and there's no sharp peak at the true random to average atom interface. That transition from true random to average atom also corresponds to the stress fluctuations in the transition from true random to coarse-grained average atom, demonstrating that the energetics are completely accurate in the spatial and chemical representations shown. We also observed the dislocation core stress profiles in the glide plane normal direction. The vertical lines at the left illustrate the position of the atomistic to continuum interface for varying widths of a fully resolved atomistic region, demonstrating that there is no discontinuity in stress that would indicate spurious forces. The stress profile is also insensitive to the number of fully resolved atomistic planes used. The solution compared to full atomistics can also be seen at the left, showing the quantitative accuracy of this approach. We then use this model to calculate the displacement versus time curves, or the dislocation mobilities. We show the curves computed for 3 randomly generated alloy seeds at each combination of stress and composition. It's clear that CAC is able to capture the essential composition-dependent behavior in these random alloys, with run-to-run variation indicative of differences in pinning positions along the dislocation line. An illustrative example of variations in the stacking fault width and wavy dislocation line configuration is also shown from CAC. In summary, CAC is an effective multi-scale approach to simulate extended dislocation line length in solid solutions. We do this with a 40% reduction in degrees of freedom, and we accurately quantify composition-dependent trends. The only thing required is an EAM interatomic potential for the alloy of interest. This work was recently accepted in computational material science, and the reference is here below for those interested. Thank you very much.